Double integrals become much easier to solve when the region we are integrating over is a circle or a part of a circle, like a wedge or a ring. In these cases, switching from xy coordinates to polar coordinates turns a messy boundary into a simple, straight-sided description. Before we see any symbols, let's say the substitution in plain words. The value x equals r multiplied by the cosine of the angle theta. The value y equals r multiplied by the sine of the angle theta. In symbols, that is, x equals r cosine theta and y equals r sine theta. Next, we need to know how area changes shape in polar coordinates. In plain words, the small area element equals r, multiplied by a small change in r, multiplied by a small change in the angle theta. In symbols, that is, dA equals r, dr, d theta. Picture the region as a flat disk on a two-dimensional plane. This is our 2D view. Now imagine lifting each point of that disk up to the height given by the function we are integrating. This creates a bowl-shaped surface. This is our 3D view. Watch how the flat circle stretches upward into this curved bowl. The polar grid of circles and rays becomes the natural grid for measuring both the flat base and the curved surface above it. Now let's work through a full example together. We will integrate the function x squared plus y squared over the disk of radius 2, centered at the origin. First, we convert the region into polar coordinates, one substitution at a time. Since the disk has radius 2 and goes all the way around, the radius r runs from 0 to 2. The angle theta runs from 0 to 2 pi, which is a full turn around the circle. Next, we convert the integrand into polar coordinates. We know x equals r cosine theta and y equals r sine theta. So x squared plus y squared equals r squared cosine squared theta plus r squared sine squared theta. Since cosine squared theta plus sine squared theta equals 1, this simplifies to just r squared. Now we assemble the full integral including the area element. In symbols, that is, integral from theta equals 0 to 2 pi of integral from r equals 0 to 2 of r squared times r dr d theta. Multiplying r squared by r gives r cubed, so the inner integral becomes integral from 0 to 2 of r cubed dr. Let's evaluate the inner integral first, the one with respect to r. The integral of r cubed dr equals r to the fourth divided by 4. Evaluating this from r equals 0 to r equals 2 gives 2 to the fourth divided by 4 minus 0 to the fourth divided by 4. 2 to the fourth is 16, and 16 divided by 4 is 4, so the inner integral equals 4. Now we evaluate the outer integral, the one with respect to theta. This becomes integral from 0 to 2 pi of 4 d theta. Since 4 is a constant, this equals 4, multiplied by the quantity 2 pi minus 0. That gives us 4 times 2 pi, which equals 8 pi. So the final answer to our worked example is 8 pi. Now for the check step to confirm this answer is correct. In Cartesian coordinates, this same integral would require a much messier square root boundary, since the circle x squared plus y squared equals 4 is not a straight line in xy coordinates. However, we can check our answer using symmetry. The average value of x squared plus y squared over the disk, multiplied by the area of the disk, should match our result. The area of a disk of radius 2 is pi, multiplied by 2 squared, which equals 4 pi, and 8 pi divided by 4 pi equals 2, which matches the expected average value of r squared over this disk. This confirms that our polar coordinate answer of 8 pi is correct.